Students, welcome to the part 2 of chapter Electromagnetic Induction. Now we are discussing motional EMF. The EMF which is induced across the ends of a conductor due to its motion in a magnetic field is called a motional EMF, which means whenever a conductor is held perpendicular to the direction of magnetic field and it is continuously brought inside and outside the magnetic field, then an EMF is induced across the two ends of the conductor. This EMF, which arises whenever the conductor is in motion in and out of the magnetic field, we call this EMF as the motional EMF. We want to find out the magnitude of this EMF using the Faraday law of electromagnetic induction. So in the figure, you can see that we have a U-shaped metal frame N, R, S and M, which is placed inside a uniform magnetic field which is perpendicular to the plane of the paper pointing in the downward direction. A metal conductor PQ is placed on this U-shaped metal frame and it is pushed towards the fixed frame RS with a certain velocity V. The length of the SR frame is equal to L. Suppose that when PQ conductor is being pushed toward the fixed frame RS at any instant of the time, it is present at a distance x from the fixed frame RS. In this case, some magnetic field lines are passing from the area enclosed by the figure PQRS. That means some amount of magnetic field lines are passing through this shaded area, and we can calculate the magnetic flux linked with this closed figure at this instant of the time, which will be equal to phi equal to flux is equal to product of field and area in this case is equal to product of the length of the frame SR and width of the frame, which is equal to x. So it will be equal to B into L into x. Now if we use the law of electromagnetic induction, induced EMF is equal to minus d phi by dt, which will give us minus d by dt of BL into x. Taking constant factors outside, we have minus dy by dt of x into BL. As the conductor PQ is being pushed toward the fixed frame RS, magnetic field is constant, the length of the frame SR is constant, so only thing that is changing with the time, it is x. And this rate of change of this distance x of the conductor PQ from fixed frame RS give us the velocity with which it is being pushed. So we can write this as minus BL into dx by dt, or we can write it as E equal to BL into V, which is the expression for the motional EMF. Here V is equal to minus dx by dt. Negative sign is there because you can see clearly from the figure that as the conductor is being pushed more and more towards the SR, the direction of the velocity is in the direction of decrease of x. So as conductor is being pushed more and more towards the fixed frame, the value of x is decreasing. So due to that, we have taken that V is equal to negative of the dx by dt. The direction of the induced EMF in the conductor PQ can easily be known with the help of Fleming's right hand rule, which says that if the index finger of the right hand points in the direction of a magnetic field and thumb is pointing in the direction of the motion of the conductor, then the middle finger will give us the direction of the induced current. So if we go according to the Fleming's right hand rule, in this case the current that will be flowing from the conductor, it will flow from end P to the end Q. That means the current in the conductor PQ, it will be flowing from end P to Q. So if it is flowing from P to Q, it will move from Q to R, then R to S, then it will move from S to P. So this will be the direction of motion of the induced current in the whole closed circuit. You can also verify that if the conductor is now pushed outside, that means if its velocity is reversed, if the velocity or the direction of motion of the conductor is reversed in the outside direction, then if you apply the right hand rule, then the same current which was earlier flowing from P to Q, now it will be flowing from end Q to P. And we know that whenever current is flowing through a conductor in one direction, it always flows from higher potential to the lower potential. This means that when it is being pushed towards the left side, because current flows from P to Q and P becomes at higher potential and Q becomes at the lower potential. But when the same conductor is being pushed in the outside direction, in that case current flows from end Q to P. So this means that end Q becomes at higher potential while P becomes at the lower potential. So in this way we can easily understand that the EMF induced or the current that is induced in the circuit due to the phenomena of electromagnetic induction continuously changes its direction back and forth. So the current or the EMF induced in this case is not direct current, but it is alternating in nature. Moreover, we can also find with little calculations the various factors. First factor is the current in the loop. The current in the loop can easily be found by using the relation I is equal to E over R. So if R is the resistance, in that case the current in the circuit that will be flowing, it will be BLV divided by R. So under this induced current, the conductor PQ is moving in a perpendicular magnetic field. That means it will also experience a force, and the force that it will experience, it will be given by ILB into sine theta, which is 90 degree over here. It will be equal to BLV over R, which is the current multiplied by length into magnetic field, which will be equal to B square L square V divided by R. Next, power delivered by the external force. Power delivered by this external force, it will be equal to product of force and velocity, which will be equal to B square L square V square over R. Last, power dissipated as a Joule loss. So if there is some resistance present in the closed circuit, some amount of the energy generated will be lost in the form of the heat energy, which we can calculate. That will be equal to energy lost. We are writing at PJ means energy lost, which is Joule loss in the form of heat. It will be equal to I square R. It is equal to B square L square V square over R square into R, which will finally give us B square L square V square divided by R. So this is the final expression for the energy loss. Thank you.